So having introduced some of the basic ideas behind set theory, I'd like to, in this video, introduce some of the axioms that are associated with set theory. And the point of this video is not to beat you over the head with axioms or be a member of the rigor police and require you to justify every single symbol that you're using or every single object that you're proposing, but to sort of from an artistic or an aesthetic point of view to see how some of the more complicated ideas in math can be built upon some of the more mild assumptions. So within set theory, there are a bunch of systems of axioms, and if you're very interested in that, then I definitely encourage you to investigate that on your own. But in this video, and probably the rest of the video series, I'll be using something called the Zermelo-Fraenkel system with the axiom of choice, abbreviated as ZFC. And this is one particular set of axioms. Namely, it's a set of 9 axioms used to set up this branch of set theory, and to once you assume the axioms, you can start to prove theorems. So it's a set of 9 axioms, but in this video I'll cover 5 of the 9 axioms, just for a reason that we won't need the remaining 4 quite yet, and we'll introduce those as we go along. So in this video I'll cover 5 of them. So from the previous video, and probably in your own mathematical life, you already have a notion of what 2 sets being equal means, what this proposition here means, A equals B. So from the previous video we said that what A equals B means is that all members of A are members of B, and that all members of B are members of A. So we've set up this proposition here, this bidirectional relationship here. So if the left-hand side is true, if A equals B, then these 2 propositions are also true. And the converse would also be true too. If these 2 propositions are true, then A is equal to B. But of course in this video we want to deal with the axioms. So in CFC, equality is going to be taken as axiomatic. If all members of A are in B, and if all members of B are in A, then we're going to say that A equals B. So this axiom is going to be called the axiom of extensionality. So here is the beast down here. So I put it down here not to beat you over the head with it, but just to get used to reading the symbols. So let's read this out. So for all sets A, and for all sets B, remember what these quantifiers mean, for all sets A and for all sets B, such that all the x's, if x is in A, if it's true that if x is in A, then that implies x is in B, and the converse, if x is in B, that implies x is in A. If that whole thing is true, if that statement is true, then this implies that A and B are equal. Alright, so that's just reading out the statement there. So that's called the axiom of extensionality, just setting up what it means for sets to be equal to one another. So hopefully that's fairly intuitive, and the symbols are starting to make sense in terms of putting all of this into precise form. So from the previous video, we also talked about power sets. We already have a notion of what these symbols here mean, what the power set of A means. Now remember, the power set is going to be that set which contains all the subsets of A. So we have some intuition about that already. So again, we want to axiomatize this. So we want to guarantee that such a set, the power set of A, exists. So in ZFC, we're going to take the existence of the power set of A as axiomatic. And very aptly named, we call this the power set axiom. So just to read the symbols again. So for all sets A, there exists another set B, such that the objects X, all objects X, if X is in B, if X lives within the set B, that implies that X is a subset of A. And that statement right there, that should be pretty familiar. That's the definition of the power set. So if X is in B, this new set B, which we're going to end up calling the power set, then that X must be a subset of A. Okay? So that's the forward direction. So the converse is going to be, if X is a subset of A, then X gets to live within the power set of B, X gets to live within this new set B, which is going to end up being the power set of A. So hopefully this bidirectional relationship makes sense. So this axiom is just guaranteeing that the power set of A exists. And from this statement I just called it B, but you can call it whatever you want. So now that you've internalized those 2 axioms, let me introduce something we haven't done yet with sets. So suppose I have some set A, which contains 1 and 2, and some set B, which contains 3 and 4. What I'm going to do is construct a set C, which contains 2 elements. First, the set A, which I've already constructed, and the second element is going to be the set B. So these two objects are going to be the entire set, A and B, not so much the elements of the set A and the set B, but the entire set A and B. So what I've done here is just substitute A and B in. So I've created this new set which pairs A with B. So I've got the old set A here, and I've got the set B here. So I've created this new set. So what I've done here is I've formed what's called the pairing of two sets, A and B, the set containing A and B. So it turns out we're going to, in ZFC, take the existence of this new set, the set containing A and B, as axiomatic. So we're going to guarantee its existence with the following axiom, called the pairing axiom, a third of our axioms. So just to read this out, for all sets A and for all sets B, there exists a new set, which we're going to call C, such that all objects of X, if that object is in that new set C, then that implies that either that object is A or that object is B. All right, so this new set we're going to call C here. If something is in that set, it's either A or it's the set B. All right, so that's the forward direction. So the converse, if that object is A, if it's the entire set A, or if it's the entire set B, it's going to be included in this new set C. So this is the pairing axiom. So it's going to guarantee the existence of this new set. All right, and this is the third of our axioms that we're going to cover. Now, if you're wondering why we care about pairing and why you'd make this an axiom within ZFC, what we're going to eventually be able to do is set up the definition of the union between two sets using pairing. So here's another new idea. Let's consider the union of only one set. Now, you're probably familiar with taking unions of multiple sets and doing tons of calculations like that, but let's consider the union of only one set. So let me construct some set I'll call A. Has two objects in it. It has a set containing 1, 2 as its first object, and the second object is the set containing 3 and 4. So let's consider the union of A. Not A and B or anything like that, just the union of A. So what the union of A is going to do, it's going to essentially combine all of the members within A. So you can see here that in the first object I have the elements 1 and 2, and then the second object I have the elements 3 and 4. So what the union of A is going to do is just going to combine all of the members of the members, so to speak. So we have, for the union of A, it's going to be 1, 2, 3, and 4. So hopefully that's pretty intuitive. So to say that again, we're going to, when we're calculating union of A, we're going to look at the members of A. That is, we saw that the set 1, 2 was a member of A, and that in that member we had 1 and 2. So we're going to stick both those elements, the 1 and the 2, in the union of A. So that new set we're going to form, after doing that process, is going to be the union of A. So this union of A, this new set, we're also going to take the existence as axiomatic. And here's our fourth axiom, called the union axiom. So just to read this out, for all sets A, there exists some other set B, which is going to end up being the union of A, such that for all the objects X, if X is in that new set B, then that implies that there's some T, there's some object within A, the set that we're taking the union of, there's some T within A, such that X is going to be within T. X is going to be a member of T. And you can practice reading the converse out too. But just to make that clear, these T's are going to be, for set A, there are only two possible values of T. There is that object 1, 2, and the 3, 4 object. So these X's are going to be included in the new set B. So the X's are going to be 1, 2, 3, and 4. And you can see that all these X's, the 1, 2, 3, and 4, these are each themselves members of the T's, which were the entire objects 1, 2, and 3, 4. So that's sort of the justification behind this, the way this union axiom is written out. So another way of interpreting this proposition here, the union axiom, is that any object X gets permission to be within the union of A if and only if it's a member of some member of A. And again, you can sort of reconcile that statement with what we've done up here in the example. So now that we have the union axiom and the pairing axiom at our disposal, I'm going to claim and show you how the common notion of the union of two sets A and B can be set up from these two axioms, the pairing and union axioms. So first, if I have two sets A and B, if you grant me the existence of those two sets A and B, from the pairing axiom I can form this new set, which is a set containing A as its first member and B as its second member. So the set right here is guaranteed by the pairing axiom. So I have that now. And then secondly, from the union axiom, I have guaranteed the existence of another set called the union of that entire set, the union of the pairing of A and B. So we've just utilized those two axioms now. So now, if I kind of analyze what the union means, so that means that if an object is going to be in this new set, the union of the pairing of A and B, that means that X has got to be within A, or X has got to be a member of the set B. Just because union means that if X is in the union, that means it's got to be a member of the set A, or a member of the set B, right? Because the pairing A and B has only two members in it, so it's got to be within A, or it's got to be within B. And it turns out that this right-hand side is what we're used to when we're talking about the union. So X is going to be in A union B if it's either a member of A or it's a member of B. So this whole right-hand side is what we're familiar with A union B. So just to summarize what we've done so far by combining the pairing and union axioms, what we said is that if X is going to be a member of the union of the set containing A and B, that implies, in a bidirectional sense, that X is either in A or X is in B. And we said that this right-hand proposition here is the same thing as X being in A union B. So what we can now do is define the operation A union B as the process of first pairing A and B as this set, the set containing A and B, and that's guaranteed by the pairing axiom. And then we can just evaluate the union of that new set that we've created. And that whole evaluation, taking the union of the set containing A and B, is itself justified from the union axiom. So you can see how, just by combining those two axioms, we've arrived at our common sense definition of what A union B means. So we've talked about 4 of the 5 axioms that I'd like to cover in this video, but the 5th axiom that we're going to cover is quite an important one. And you'll see that after introducing this axiom, we can justify the existence of the empty set. And just like we define A union B, we can now define A intersect B after introducing this 5th axiom. So one other thing we'd like to do in set theory is, if we have a set already constructed, we'd like to decompose or analyze the set. We want to break into its parts. So consider the set A containing 1, 2, 3, and 4. And suppose I wanted to construct 2 new sets. How about the set B containing only the even numbered elements in A? So that would be 2 and 4. And correspondingly, some other set C, which contains only the odd elements that were in A. So I'd like to sort of axiomatize this whole process of, once we've guaranteed the existence of some set, we want to be able to break into its parts. We want to guarantee the existence of these new sets. So this new axiom, what it's going to allow us to do is select the members of A as we'd like. And it turns out that this axiom is very aptly named the axiom of subsets, because you can see that each of these sets, B and C, are themselves subsets of A. And this axiom is also called the axiom schema. Schema because it's really a list of axioms. It's a whole family of axioms, not just one. It's called the axiom schema of separation, in the sense that I can separate elements away from the original set. So again, just to read this out, for all sets A, there exists some new set B, such that all the x's, if those x's are members of B, that implies that X is a member of the original set A, which we've kind of assumed to exist, and it meets some other requirement. And I'm going to leave this in the vague sense, because this requirement can really be just about anything. So in this case, when I constructed these new sets, my requirement for B was that its elements not only be within the original set A, but that these x's also be even in the case of set B. In the case of set C, I wanted them to be odd. So to be even or odd, those are just two examples of requirements that I may place upon X. So using our set builder notation, we can also write the previous axiom in the following form. So suppose I have some newly created set C. Now this is going to be all of the objects X such that those objects are in some other set A and ... some other condition. Now this is that sort of vague condition that I left as vague because it can be anything you like. Now if we make the restriction that in this ... that this X has also got to be within B, and I can see that this such that condition is X has got to be within A and it's got to be within B. So I get C has got to be all the X's such that X is within A and it's also within the set B. So what is this? This is our common sense notion of intersection between two sets. So you can see that this newly created set C, I'm going to essentially define this as A intersect B. So you can see from the axiom of subsets, I can now retrieve a precise definition of intersection between two sets. Now suppose I change up this restriction. We just had it be X, B, and B, but suppose I make the restriction X is not in B. All right, so this condition would be C is all the objects X such that X is in A and it's not in B. Then what is this? So from the previous video, hopefully this sounds pretty familiar. So this is the complement or set subtraction. So this new set C is going to be all the objects in A and all the objects in B subtracted out of it. So it's going to be the relative complement of B and A. That's another way of saying it. Or it's just A minus B, like you're familiar with. So those were two examples of restrictions that I could put in that ... within the subset axiom. So suppose I substituted something kind of bizarre into that. What if I substitute the restriction that X is not equal to X? Okay, so our new set C, which by the way is guaranteed to exist, it's all the objects X such that X is in A, which is some other set that we've assumed to exist, and the requirement that X is not equal to X. So my question is, what objects X satisfy that requirement? So the answer is that none. There's no object that satisfies that requirement, just because this is a contradiction here. X is not equal to X. So C is going to be the empty set. So since no objects satisfy that condition, and we've said that this set has got to exist by the subset axiom, then the set can't have any members in it, aka the empty set. So what I'm arguing is that the subset axiom guarantees the existence of the empty set. But if you found that to be kind of bogus, you could also take the existence of the empty set as axiomatic too. And in some textbooks you'll just see that. But the empty set axiom, as it's sometimes referred to, it can be derived from some of the other common axioms used within set theory. So before concluding this video, I'd like to make a few final notes on intersection as an operation. So just as we calculated the union of only one set, we can also calculate the intersection of just one set. And this is going to turn out to be very analogous to the union of one set. So we're going to say that the intersection of one set A is all the objects X, such that X is a member of all the members of A. Okay, so that's the entry condition. If X is a member of all the members of A, it gets permission to be in the set intersection of A. So another way of saying this is that X gets to live within the intersection of A if and only if, for all T's that are in A, all these members T within A, X is also in T. So both of those have to be true, all right? So that's the forward direction, and then of course you want to practice reading the converse as well. So this proposition here is equivalent to set builder notation, so just to get you to read the symbols. Now be sure to contrast this with our definition of union of A. So this is all the X's such that X is a member of some member of A. It could be one member of A, it could be two members of A, could be all of them, but just one, at least one. Now the intersection of A requires that X be a member of all the members of A. So make sure to contrast those in your head. So in symbolic form, the definition of the union of A is very similar, except you have, in this position, you have the existential quantifier instead of the universal quantifier. So this should make sense because there should just be one. If there's at least one t, there exists some t such that t is in A and x is in t. Then x gets permission to be in the union of A. So just to make sure that the idea is clear, the idea of taking an intersection of just one set, let's consider an example. Let's say I have some set A, has two members in it. First it has 1, 2, 3, the set 1, 2, 3, and its second member is a set 2, 3, 4, 5. So looking at the definition of the intersection of A, I'm looking for all the x's such that x is a member of both this object here and this object here. So what do those two members of A have in common? So those x's have permission to be within the intersection of A. And you can see pretty clearly, hopefully, that those two elements are the numbers 2 and 3. And just as we showed that the union of the pairing corresponds to our common sense definition of A union B, we can also show that, and I'll leave this as an exercise for you, that the intersection of the pairing corresponds very nicely to our common sense notion of the intersection of two sets. So that wraps up this video. Here are some practice problems. Notice that the first problem is precisely what I asked in the previous slide. And some of the other ones are just review from the previous lecture, just working with power sets and starting to work with some of the algebra behind sets. So if you enjoyed the video, give it a thumbs up, leave a comment below or subscribe or whatever, and stay tuned for the next video. Thanks.